Good morning. Today I'm going to introduce you to the concept of Lewis dot structures. Before we begin, make sure that you have a periodic table that you can use, as well as have this opened on one of your tabs, the Lewis dot structures packet. There's a link for it in the modules. The first thing I want to remind you of is when we were looking at the periodic table, one of the things we said you could do was that you could label the 8 tall columns left to right, 1 through 8, and that would represent the number of valence shell electrons in those columns. For example, we said that the alkali, as well as hydrogen, had 1 valence shell electron, which I'm going to abbreviate VSE. The column with beryllium, the alkaline earth, had 2 valence shell electrons. Boron's column had 3. Carbon's had 4. Nitrogen's column has 5 VSEs. Oxygen's has 6 VSEs. The halogens, 7 valence shell electrons. And then finally, the noble gases have 8 valence shell electrons, except for helium. Helium only has 2. One other thing we said was we had talked a little bit about the octet rule. And the octet rule states that atoms are most stable when they have 8 valence shell electrons, which makes them like the noble gases. In ionic compounds, we talked about how they could lose electrons to get back to the prior noble gas, or they could gain electrons to get to the next noble gas. Well, what we're going to look at today is how the octet rule is satisfied when we're dealing with covalent compounds. In covalent compounds, instead of losing and gaining electrons, atoms share them. So the first thing we're going to do today is talk about how we can determine how many valence shell electrons are available for a given element. You may remember from middle school actually drawing these Lewis dot structures for simple elements and for some compounds. So the first thing I'd like you to do is to pause this video for a second and determine how many valence shell electrons you would expect to have in these elements. So take a second and do that. I'm going to pause it for a sec. Okay, so let's go ahead and check your work. You should have had 3 for boron, because it's in this column, 3, 1 for hydrogen, 6 for selenium, which is right here below oxygen, so it should be 6, 4 for silicon, 5 for nitrogen, 7 for chlorine, and 8 for krypton. So what do we do with that? Well, initially, we start by drawing the Lewis dot structures of individual atoms. For example, boron has 3, and the way that we draw Lewis dot structures for atoms is we represent those electrons as dots. So boron has 3 valence shell electrons, so I'm going to give it 3 dots. Hydrogen has 1 valence shell electron, so I'm going to give it 1 dot. Now, it doesn't really matter on which side I put the dots, but do notice on boron, I spread it out to 3 sides. I didn't double it up. Selenium has 6, so I'm going to put 1 on each of the 4 sides before I double up. Now, the sides I double up on don't matter so much, but you'll notice I've used a total of 6. So take a second and see if you can do the other 4 on here. And so pause this and then come back and check your work. You should have had 6 for silicon, 5 for nitrogen, like that. 7 for chlorine. Once again, it doesn't really matter which side you leave with the single. It could have been on any of the sides. And then, of course, krypton has 8. Now, just to touch back on what happened with ionic compounds, remember that we said that they can gain or lose electrons to get to their nearest noble gases. So, for example, boron starts with 3. Does it make more sense for it to lose 3 to become like the prior noble gas, which in this case would be helium? Or does it make more sense for it to gain 5 to get to neon? Well, the basic rule is if it's in the middle at 4, it can go either way. But if it has 3 or less, it loses those electrons. If they have 5 or more, they gain to get up to 8. So when we make boron's ion, it's going to lose those 3. We're going to put it in little brackets to show that it's just empty. And what will its charge be? Well, remember that electrons are negative. So if you lose 3 electrons, your charge will be -3. How about hydrogen? I'm sorry, +3. I'm just trying to confuse you here. Yeah, if it loses electrons, it becomes positive. So hydrogen has 1, it's going to lose that. So what will its charge be? +1. Now, selenium is at 6. Remember we said if they had 5 or more valence shell electrons, they tended to gain to get up to 8. So what will its Lewis dot structure look like when it's gained? Well, instead of having 6, it will now have 8. And how many electrons did it gain? Well, it gained 2. So what will its charge be? -2. So try the next 4. See if you can figure those out on your own. Will they gain? Will they lose? Either take them up to 8 or drop them to 0. And no matter what you do, you have to correct the charge. Well, hopefully you paused and tried that on your own. Let's look now at what these will be. So silicon had 4. So silicon has 2 choices. And you could have drawn either one. It can either gain 4 electrons and have a charge of -4, or I'm going to draw it out over here to the other side. Silicon can lose 4 electrons and be +4. Hopefully that makes sense to you. You can either gain 4 to get to 8 or lose 4, and then its next row in is like a noble gas. Nitrogen has 5, so it's going to gain 3 more and be -3. Fluorine has 7, so it's going to gain 1 more and be -1. And krypton already has 8, so it is good just as it is. So there's a little bit more of a close-up of those. So the next thing that we're going to look at is how do we determine the number of valence shell electrons available for a compound or a polyatomic ion. So as you can see right here, I did 2 examples. Carbon dioxide has a carbon and 2 oxygens. So what we're going to do is add up the total number of valence shell electrons available. Because carbon is in this column, it's going to have 4. I've got 2 oxygens. They each have 6. So you can see where I got those numbers. So that we say that oxygen has a total of 16 valence shell electrons. Phosphate is one of the polyatomic ions we've been dealing with. It's got a phosphorus and 4 oxygens. So the phosphorus is below the nitrogen, so it's going to have 5, just so I can reiterate where I'm getting that from. Phosphorus is in the 5 column. My oxygens are in the 6 column. So I'm showing 5 from the phosphorus, 6 from each of the 4 oxygens. And the fact that this phosphate is -3, what that means is that it has gained 3 additional electrons to make that structure work. So the way I represent that is by adding 3 extra valence shell electrons to my total. So 5 plus 4 sixes plus the 3 from the negative charge means that this structure has 32 valence shell electrons. So I would like you to try adding these up. Go ahead and take a second and pause. Add these up. Just to remind you, this is Cl, chlorine, not Ci. Pause this and then come back and we will check your totals. Okay, so for ammonia, nitrogen is 5 plus 3 hydrogens each have 1, so this is 8. You should have gotten 26 for the SO32 minus sulfite. You should have gotten 32 for the SO42 minus. You should have gotten 10 for the CN1 minus. And you should have gotten 14 for the CH3Cl. So that's the first step in drawing Lewis dot structures, is determining how many valence shell electrons you have. So I'm going to end this video for now. But I will post a second one that shows you how to start drawing the actual structures themselves. Thank you very much.